Hello, on behalf of Team RNH, I present to you a low-cost wireless satellite hub which provides optimum performance. For every engineering problem, we have to deal with some trade-off. These are the few design constraints and assumptions we have made in this project. The device has a separate command line on which it sends to the hub a command signal that contains information regarding the device ID, data size, tag, and read-write command. The device can either request data or send data from or to the hub at a time, but it cannot do both simultaneously. Any data sent to the hub by the device is directly sent to the data center in case the memory is found to be full. We have had to utilize part of the 256-byte memory for storing memory address, tag, and valid bits. After a survey of the provided test cases, we could infer that the request for reading and writing a data of transaction size 512 bytes was minimum. That for 128 bytes was second popular, and that for 1024 was most frequent. In an attempt to ensure minimum unit cost coupled with minimum communication cost, we have made the following decisions regarding the memory architecture. Our hub is divided into 6 blocks of memory. Memory M1, which has a capacity of 256 bytes, 2 memories of type M2, with each having a capacity of 512 bytes, and 7 memories of type M3. M3 has a capacity of 1 KB each. Apart from these 3 memories, we have made use of 6 16-bit buffers to store the request sequence. The input from the device contains the following: the device ID, read or write signal, data size, the tag, and the input data. The output of the hub would be output of the hub to the device would be data out and the value of the clock that was required to compute the to complete the transaction. The memory M1 has a capacity of 256 bytes. This memory was sectored into 2 portions of 128 bytes. The lower 128 bytes of memory is used to store a single data of size 128 bytes. The upper portion is divided into 2 sectors: the tag address memory and the valid bit memory. The tag address memory contains memory addresses that correspond to a particular location where the data for a particular tag is stored. The valid bit memory contains the valid bit indicating whether a particular memory location is occupied or not. The tag address memory is divided into 26 rows of 16 bits each. The 16 bits are divided as 5 bits for memory address. This is the address that we have named each of the memory locations or slots. The 5 bits for tag that is specified by the device, 2 bits for data size, and 4 bits that are redundant. We have used the 4 redundant bits to provide ease of access and flexibility to expansion of the system. The valid bit memory, since we have divided the entire system into 27 memory blocks, then there is 1 bit corresponding to each memory slot. That is from V0 to V26. We have made use of 7 memory blocks that are 1 kilobyte long. Out of those 7 blocks, 2 of them have been sectored into slots of 128 bytes. The bits VNE1 and VNE2 are used to indicate if those 2 1 kilobyte blocks are filled or not. A value of 1 would indicate that 1 or more locations are filled with 128 bytes of data, or the entire location or entire memory is filled with a single block of 1 kilobyte data. If it is 0, then the entire block is empty. We have made use of 2 memories of capacity 512 bytes each. We together name it M2. One memory of 512 bytes is dedicated to storing data of transaction size 512 bytes. The other memory is sectored into 4 slots which can hold up to 128 bytes each. To summarize, memory M2 can hold 4 data of size 128 bytes each and 1 data of size 512 bytes. We have used 7 memories of type M3, each having a capacity of 1024 bytes, and now we are going to together name it as M3. 5 memories of M3 type are dedicated to storing 1 kilobyte long data each. 2 memories are sectored into 8 slots of 128 bytes. These can store either a single 1 kilobyte data or 8 different 128 bytes long data. So, in total we have 26 different memory locations and we require 5 bits to represent these. We have implemented this system using Verilog programming, and the system is implemented using 6 different modules. A scheduler module. This is used to queue the incoming device connection request and to process in parallel the request of the device first in queue. The queue is implemented as a simple first in first out buffer. Second, we have made use of an address decoder module. In this module, we determine the memory address at which the requested data is located in case of reads. Or, in case of writes, we find an available memory location. This module returns a memory address value. The third module is a hub controller. It decides which memory module is to be invoked depending on the memory address value returned by the address decoder module. Apart from these, we have 3 different modules for the 3 memories M1, M2 and M3. These memory modules perform the basic read and write in their respective memories. When a device intends to send or request data from the hub, it sends a request for connection signal to the scheduler. The scheduler in turn queues these device requests as they come into the queue buffer. Once the scheduler sends a request for processing, it sends an acknowledged signal to the device, saying that now the device is connected to the controller and the command as well as data in must be supplied by the device to the controller. The controller performs the processing of the signal. It first collects data from the device, it collects the command line from the device and forwards this command line to the address decoder. The address decoder uses a tag found from the command line supplied by the device to determine the internal memory address where the corresponding data is stored in case of read or where the corresponding data must be returned to in case of writes. This memory address is returned to the controller. Based on the memory address value obtained, the controller decides which module M1, M2 or M3 must be invoked. When the scheduler module schedules a request, controller module takes data and command input from the device. It then sets the enable signal for the address decode module invoking it. Based on the memory address returned by the address decode module, if the memory address value is 0, memory 1 module is invoked by setting its enable. If the value lies between 1 and 4 or the value is 26, then memory module 2 is invoked by setting its enable. For address values that lie between 5 and 25, memory 3 module is invoked. Once these 3 modules have finished their working, they indicate that they are free by returning a busy signal to the controller module. If the value of the busy signal is 0 from all the 3 modules, then the controller is ready to process the next sequence of requests. The address decoder module. For a request to read data from the hub, the module compares the tag obtained from the device command and the tag value stored in each row of the tag address memory. If there is no tag match, a miss is indicated and the data must be fetched from the data center. This is achieved by passing a 32-bit command that contains the device ID, data size, tag, and read-write signals. Apart from this, it has 22 redundant bits for future use. In case of a request to write data to the hub by device, the valid bits in the valid bit memory are checked one after the other to determine the first available memory location. As soon as the slot is found empty, the memory address is returned to the controller module. If there is no free space available, a value of 31 is returned to the controller, which in turn directs a 32-bit command to the data center via the satellite. Data is then returned to the satellite. The basic concept of the memory module is that the data of appropriate size is read from the memory address value determined in the address decoder module. or it is returned to that particular memory address that is returned by the decoder module. This is a test cases and benchmarks file. Since we have used one memory of type M1, two memories of type M2 and 7 memories of type M3, our total cost was summed up to $91. So our hub can be purchased at a cost that is less than $100. The maximum latency seen was 7.5 into 10 raised to 9 clock cycles, that is 7.5 giga clock cycles. This is a demo of the address decoder module. In this address decoder module, on the command line, we are giving the tag. The tag is determined from the command line here, and then the output of the address decoder is memout, where we are returning the value of the address location where the data transaction from which the data transaction must happen. Also, we have made use of an internal clock counter, that is counting the number of clocks that were required for each memory transaction. This is a demo for the memory module M1. The memory module takes into consideration of the data size and the memory address value returned by the address decoder module, and performs read and write operations at those particular memory addresses. Since memory module M1 deals only with 128-byte transaction size, therefore it runs only when the data size is 0. Other times it returns a busy signal. It returns a low value for the busy signal, saying that the module is free. This is the transcript for the test set 1. It shows it shows the connection status of the devices, and in case of memory full, what we must do, that is retrieve data from the data center and all. This transcript shows the performance of the controller module. And lastly, these are a few proposed enhancements which, if given time, we were going to implement. That is, one would be parallel processing of data requests and send for the same device. Receiving or sending serial data from or to a device while executing another request in parallel, and using an eviction strategy. Thank you.